Hi, my name's Matt Dolan and welcome to this talk on certificate pinning and its replacement, certificate transparency. Let's start by asking ourselves, how secure is a secure connection? HTTPS does a pretty good job, however there's one thing we need to be aware of when a connection is established. The first thing that happens when establishing a secure connection is the client sends a hello message along with a list of supported encryption ciphers. The server replies with its hello message, picking a cipher, and presents the client with its certificate. The certificate identifies the server as the one you've connected, and it's up to the client to verify that the certificate is valid. The client then builds a certificate chain using the leaf certificate retrieved from the handshake as a starting point. The issuer distinguished name from each certificate is used to find its parent certificate until we find a root certificate which is installed on the client's device. The public keys contained are used to verify the signature of these certificates, building a trusted certificate chain. The idea that a root certificate is installed in the client first originated in the Netscape web browser in the 1990s. This decision by Netscape means we implicitly trust the root certificate, and that means we trust the certificate authorities who generate and sign these root certificates to only issue certificates to people who own a given domain. Now, given these two certificate authorities, which do you trust? Both have the word trust in their logos, so surely we trust both of them. Unfortunately, both were hacked in 2011. With DigiNotar, this resulted in a rogue Google.com certificate in circulation for more than 5 weeks. And for those 5 weeks, the person who created those certificates could pretend to be Google and gain access to their encrypted network traffic. While there is nothing inherently insecure about HTTPS, the system is built on the trust of those root certificates, which is why standards such as certificate pinning gained popularity. So how does certificate pinning stop this kind of attack? The simplified version is that pinning uses a hash of the public key to verify that a particular certificate appears somewhere in the chain, and if it doesn't, then the connection is denied. From a technical perspective, implementing pinning looks pretty trivial, requiring just a few lines of code. However, the code doesn't really show us the complete picture. There are certain questions you need to answer, such as which certificate do you pin, how you handle compromise, and what happens if you need to change your public key. Get this wrong and you risk breaking your app. While this is an example from the web, Smashing Magazine famously blocked access to some of their users for a year in 2016 when they knowingly updated their website certificate and thus the pins. Incidents like Smashing Magazine led Chrome to deprecate support for pinning in July 2018. And while no modern web browser supports pinning anymore, it still remains popular on mobile because little is known about its replacement. This is where certificate transparency comes in, first standardized by Google in 2012 with support in most major web browsers. Certificate transparency has 3 aims: make it hard to issue certificates without the domain owner's knowledge, provide auditing and monitoring to spot misissued certificates, and protect users from misissued certificates. When a new certificate is created, it is publicly logged to at least 2 log servers. Log servers are append-only and use a Merkle tree hash to prevent tampering and misbehavior and to aid auditing and monitoring. In the case of DigiNotar, we would be aware of a new certificate within hours, not weeks, allowing us to react quickly and get those certificates revoked. So, does certificate transparency work? The short answer is yes. It's helped companies such as Facebook and Google spot misissued certificates for their own domains, including one created by a trusted certificate authority for, well, quote, testing purposes, because we've all heard that excuse before. So how do we go about using it ourselves? The most important part is actually the ability to be able to monitor your own domains and detect misissuance promptly to be able to take the necessary steps to get rogue certificates revoked. Now, I've listed a couple of tools you can use for free, however, of course there are others. And it's worth noting some tools will actually help you spot certificates being created for things like phishing domains. Now let's look at how client verification works. While there are 3 ways a client can receive information about the logging of certificates, we're only going to cover the most common, which is embedded in a certificate. When we ask a certificate authority for a new certificate, it submits a pre-certificate to at least 2 log servers. The log servers return a signed certificate timestamp, which is a promise that the certificate will be added to the log server within the next 24 hours. These signed certificate timestamps are then embedded into the certificate that the certificate authority provides to our server. Now, when establishing a connection, as a basic check, the client uses the public key of the log server involved to verify the signature of that signed certificate timestamp. If there are discrepancies, the client will reject the certificate and close the connection. Unlike certificate pinning, there is no reliance on your certificates, whether that's the public key used or the certificate authority you have chosen. So let's see how to implement certificate transparency on mobile. On iOS, there is built-in support using App Transport Security, which means we can implement certificate transparency with a couple of lines of code. However, on Android no such support exists, and while Google's Conscript library has code for certificate transparency, it's hard and very hacky to try and get it working. This lack of official support is what led me to write and release my own open source library in 2019. Certificate transparency is even easier to configure than certificate pinning, as no configuration is necessary to enforce certificate transparency checks across your app. The single line of code shown here installs a custom Java security provider that performs these checks. Broadly speaking, the library caches a list of log servers from Google as used in Chrome. This list provides details of the log server's public keys, which are then used to verify the signed certificate timestamps presented when you make a secure connection. I want to finish on an important point. Certificate transparency makes it easy to spot misissuance, but it doesn't prevent it. Ultimately, it's your responsibility to get a certificate revoked. However, Android doesn't handle certificate revocation. It typically requires additional network calls that can be compromised, so there's more work we need to do as a community to build secure apps. For more details about certificate transparency, check out the project on GitHub.